So as promised, I'd like to go over the new concepts for this week in a quick video, just in case you didn't get it at the end of class. But basically, going over this essential question still doesn't make sense as written, but how much heat is involved, maybe. Heat is transferred whenever a phase change is involved. In class, I briefly went over the phase diagram, where on the x-axis I have the amount of energy added to the system, and on the y-axis I have temperature, and we had the example of going from an ice cube into gas. So as I add energy, like put the ice cube to a fire or warm it up in your hands, the temperature of that ice cube increases, as you would expect. So it increases at some rate that's actually dependent on specific heat, but it increases until it hits 0 degrees Celsius, at which point, some of you astutely noted, it should start melting. But the interesting thing was that the melting line became flat. That means literally, as you put that ice cube up to the flame or add more energy to it, the temperature stays the same, stays at 0 degrees Celsius for a little while. And then eventually it melts and becomes liquid proper, and then the heating resumes, as you would expect. As you add more energy, have a boiling pot of water, or a pot of water you're trying to boil on the flame, temperature will increase until, again, you reach 100 degrees Celsius, which is boiling. Again, these numbers will actually differ depending on the substance, because everything has a different boiling point or melting point, but they will all flatline like this, at least for some amount of time. The length of the horizontal line will depend on its heat of fusion, which we'll talk about in a second. But it'll boil and stay at 100 degrees. You can't boil water hotter than that, no matter how much fire you add to it. And then, beyond that, it's a gas. And then the gas's temperature will increase if you add more and more energy. So, this phase diagram, again, I said in class that these slanted parts of the line, that's where you use Q equals mc delta T. You're just changing it and going up and down these lines. You can't use it between different parts of it because the value for C, the specific heat capacity, will change depending on the specific substance, and will even differ for a substance in different phases. So like C of liquid water is different from C of solid water or ice. But you can use this formula for each individual part where it's just solid, just liquid, or just gas. When you encounter these horizontal parts, though, where it's melting or boiling, you'll actually need to use a different, it's not quite a formula so much as a different concept. You won't use C. Basically, for Q equals mc delta T, you're taking its specific heat, the amount of heat you need to warm up a certain amount by a certain temperature, and multiplying it by the amount and the temperature to get just the amount of energy. It's kind of dimensional analysis in that sense. Likewise, for these two, you'll need something called the heat of fusion and the heat of vaporization. So, I mentioned that heat of fusion is a fancy term for the amount of energy you need to melt something, whereas heat of vaporization is the amount you needed to boil it. But, sorry, you can't quite see that, but the amount you need to boil it. Both of them are given in units of energy per amount. I know here it says energy per mole, but you might actually get it as energy per gram or energy per kilogram. So any of the following are valid. I could give it to you in joules per mole. I could give it to you in kilojoules per gram. I could give it to you in joules per kilogram. It doesn't really matter, as long as it's energy per amount. If you have more stuff, you need more energy total. But you need to do this, you need to have these heats of fusion and vaporization so that you can break the intermolecular forces, or the things that are holding solids together to make them solid, the things that hold liquids together to make them liquid. You need to kind of give them that extra push in terms of energy to get it to the next phase. So for liquids, those are the IMFs we've talked about, these dotted pink lines I'm drawing in. These hold them together to like make the liquid different from a gas. It holds them together because liquids stay together, more or less, unlike gases. And to break those bonds, that's what's happening when you add energy at the vaporization point. When it's vaporizing, you're breaking these intermolecular forces. Likewise for the solids, they're in this kind of crystal lattice. That's what defines a solid. And to kind of pop them out of place, pop them out of their low energy state, you need to give them a little bit of extra energy. The details of which we won't get into for chemistry 1. But basically you follow this phase diagram, this curve, and decide what equations you need to add together. You need to add together all like the different heats that you're adding whenever you change the temperature of a substance from point A to point B. Very specifically, what that means, I'm not going to do all the progress problems here. You can kind of try some on your own or see what I've written on the slides, but very briefly, to get from this starting point that I have in green down here to this ending point, first I'm going to need to calculate this first segment with Q equals mc delta T, using the C for ice. Then I'm going to need to add that to the amount of energy in blue right here, which is going to be using the heat of fusion. And finally, I'm going to need to add that to this final segment where I heat up just liquid water again, using the C for water. The blue, green, and pink quantities will be added together. Whenever you add something, you want to make sure the units are the same. So you'll probably get joules for the water and joules for the ice because of these joules are on top. Notice that the fusion is in kilojoules, and it doesn't make sense to add them in the same way that you wouldn't add like 3 meters plus 1 kilometer is like 4 kilometers or 4 meters. That just doesn't work. You need to convert them to the same unit when you add. So just be aware of that. I'll also just skim some of the other problems out loud. So, which state of matter changes temperature the easiest? What does that mean? So, which of these quantities are associated with the state of matter? Again, you can pause and think about it. But these three right here, these specific heats talk about changing temperature while you're in a specific phase. These two are for transferring between phases. But you can see the lower it is, the less energy you need to add for it to change by 1 degree Celsius. Again, you can think of this as 1.70 joules per 1 gram per 1 degree Celsius. 1 degree Celsius. You only need that many joules. So in that sense, steam changes temperature the easiest. And that you can see that actually by the slope of the line on the phase diagram, but we're not going to get into that in too much detail. You can also do more involved problems. This is very much like the example that we did earlier. Here's your start point, there's your end point. How would you figure this out? You'd again need to break it up into 3 parts. Notice that these are actually from the thermo exercises packet. So we will work through some of the problems there, but there's not going to be enough time to do all of them. So I'd strongly encourage you to get started on your own time. This is the same question, but we don't give you the phase diagram this time. You kind of have to envision it in your head. Hint, because you're going from water to... Oh no, you're going from ice to steam. It's going to take a lot more than 3 steps this time, unfortunately. I think it'll take you 5 steps. And yeah, I think the rest are pretty similar. This one's kind of fun. I'll probably go over it in class. Right. So you should be able to solve all these problems just given the concept that we've learned now, along with Q equals mc delta T. Okay, I will see you all on Wednesday, and I probably won't make another video on Wednesday just because it's going through practice problems like we will in class. If you have any feedback, please let me know. Otherwise, see you then. Bye.